3I Atlas has just been recharacterized, and the new data sharply change how the object must be interpreted. Direct observations now show that it is far larger than previously estimated, that its activity after perihelion does not follow standard comet behavior, and that it produced methane in a sequence that contradicts established volatile physics. Its trajectory also deviated in ways that are difficult to reconcile with its revised mass. These findings are no longer based on inference but on direct measurement. Taken together, they place 3I Atlas outside existing physical models and force an immediate reassessment of whether current frameworks are sufficient or whether additional, rarely observed natural processes must now be seriously examined. The reassessment begins with the nucleus itself. For much of the object's passage through the inner solar system, its size could only be estimated indirectly. The coma dominated the signal, and brightness-based models suggested a relatively small nucleus, close to 1 kilometer in diameter. That assumption shaped nearly every downstream interpretation. It made the observed activity levels plausible. It allowed non-gravitational acceleration to be explained through conventional outgassing. It kept the object within the statistical and physical boundaries of known comet populations. That assumption has now been replaced by direct measurement. Post-perihelion observations collected between December 2025 and January 2026 by the Hubble Space Telescope resolved the nucleus with sufficient clarity to constrain its size. The analysis indicates a diameter of approximately 2.6 kilometers, with an uncertainty of about 0.4 kilometers. Even the most conservative interpretation places the nucleus well above 2 kilometers. At the upper end, it approaches 3. This measurement was reported in a peer-reviewed study led by an international team that includes David Jewett, whose work on comets and small bodies has defined much of the modern field. This increase in size is not a minor correction. Because mass scales with the cube of diameter, the revised measurement implies a nucleus roughly 27 times more massive than estimates, still circulating late in 2025. Compared to 2I Borisov, the only other confirmed interstellar comet, the inferred mass difference is on the order of 40 times. Objects in this mass range behave differently under solar heating. They retain volatiles differently, resist acceleration more strongly, and respond to thermal stress on longer timescales. Many explanations that were viable for a 1-kilometer object become strained when applied to a body nearly 3 kilometers across. The consequences of this revision are immediately visible in the activity data. As 3I Atlas approached the Sun, it brightened in a manner consistent with volatile sublimation. That behavior alone did not distinguish it from an ordinary comet. The divergence appeared after perihelion. Following its closest approach on October 29, 2025, the object faded more rapidly than its pre-perihelion trend would predict. The decline was not gradual. Surface brightness profiles show a post-perihelion coma that is significantly shallower than its pre-perihelion counterpart, indicating a rapid reduction in activity once the object began moving away from the Sun. At the same time, temporal variations in brightness persisted. The nucleus-like light curve exhibited ongoing fluctuations, indicating that activity did not simply shut down. One plausible explanation is rotation modulation, in which active regions rotate in and out of sunlight. However, earlier observations complicate this interpretation. Prior to perihelion, the pulsing behavior appeared to occur at a rate faster than the inferred rotation period. This suggests that rotation alone cannot account for the observed variability, and that additional processes were influencing the release of material from the nucleus. The most consequential information, however, came from spectroscopy rather than imaging. After perihelion, the object was observed with the James Webb Space Telescope, which provides direct sensitivity to volatile species and molecular emissions that optical telescopes cannot reliably detect. Webb observed 3I Atlas at heliocentric distances of approximately 2.2 and 2.54 astronomical units, producing the first detailed post-perihelion spectroscopic characterization of the object. Those observations revealed a significant shift in composition. Water vapor became much more prominent than it had been earlier, while carbon dioxide declined. This represents a reversal of the pre-perihelion state, when carbon dioxide dominated the coma and water was present only in small amounts. Compositional evolution across perihelion is not unusual in comets, but the magnitude and timing of this reversal were notable, particularly when evaluated alongside other chemical signatures. Nickel continued to appear in large quantities. Nickel detections in cometary comae are rare, and sustained abundance is rarer still. Iron, which had not been detected earlier, appeared after perihelion, but the ratio between nickel and iron was highly anomalous. It fell well outside the range measured in any known solar system comet. While theoretical mechanisms exist that could produce elevated nickel abundances through natural processes, no observational precedence has been established. Comparable ratios are commonly encountered in industrial or high-temperature processing environments, not in cometary nuclei. The most consequential chemical anomaly emerged with the detection of methane. Methane is a hypervolatile compound with a sublimation temperature lower than that of carbon dioxide. Under standard thermal models, methane should be among the earliest species to appear as an icy body approaches the sun, and it should decline as solar heating decreases. In 3I Atlas, methane followed the opposite sequence. Methane was absent in early observations, even as carbon monoxide and carbon dioxide were clearly detected in substantial quantities. This absence is significant because methane is more volatile than carbon dioxide and should sublimate at lower temperatures. Under standard thermal models, methane should therefore appear at least as early as carbon monoxide and typically earlier than carbon dioxide as an icy body approaches the sun. Instead, no methane signal was detected during the pre-perihelion phase when solar heating was strongest and volatile release was most efficient. Methane emerged only after perihelion, once the object had already passed its point of maximum solar irradiation. More notably, its relative abundance increased as the object continued to recede from the sun. Quantitative analysis shows that during one post-perihelion observing epoch, methane production reached approximately 13.7% of the water production rate. In a subsequent epoch, at a greater heliocentric distance and lower solar input, methane production rose further to roughly 27% of the water production rate. This trend is the inverse of what established volatile physics predicts. In conventional cometary behavior, hypervolatile species are expected to peak near perihelion and decline rapidly as solar heating decreases. As distance from the sun increases, sublimation fronts retreat deeper into the nucleus, reducing the release of the most volatile compounds first. Methane's late onset and rising production therefore contradict the expected thermal sequence. Any model invoking surface or near-surface sublimation fails to reproduce this behavior without introducing additional assumptions, such as delayed exposure of deep reservoirs or non-thermal release mechanisms. Even then, these explanations remain in tension with the simultaneous early detection of more volatile species, leaving the methane sequence fundamentally inconsistent with current cometary models. Several natural explanations have been examined. One hypothesis proposes that methane was depleted in the outer layers of the nucleus and remained trapped deeper inside until continued sublimation exposed fresh material. However, this scenario conflicts with other observations. Carbon monoxide is more volatile than methane and should have been lost first if the outer layers were depleted. Instead, carbon monoxide was detected early, while methane was not. This inversion of expected volatility behavior remains unexplained by current models. At present, no accepted natural explanation accounts simultaneously for the timing, abundance, and evolution of methane production in 3I Atlas. This chemical anomaly intersects with a broader line of inquiry raised by Avi Loeb. Methane is a molecule strongly associated with biological processes on Earth. Its presence alone does not imply life, and it is not treated as a biosignature in isolation. However, the delayed appearance of methane, its increasing abundance with distance from the sun, and its coexistence with water and carbon-bearing compounds form a pattern that is difficult to reconcile with known cometary chemistry. Loeb has framed this as a boundary case rather than a claim. When conventional physical explanations appear insufficient, alternative hypotheses, including biological ones, become permissible to consider, though not favored without supporting evidence. In this context, methane is treated not as proof, but as an unresolved signal. The discussion naturally extends to panspermia, the hypothesis that life or prebiotic material could be transported between star systems. Such ideas remain speculative, but they arise directly from the inability of existing models to account for the observations without invoking increasingly constrained conditions. Independent of its chemistry, the object's motion presents another challenge. As 3I Atlas passed through perihelion, its trajectory deviated from predictions based solely on gravitational forces. Part of this deviation can be attributed to the sun's influence, but a residual component remains. This non-gravitational acceleration is typically explained by outgassing, which produces a recoil force as material escapes the nucleus. Here again, the revised size of the nucleus complicates the explanation in a fundamental way. Models that attempt to reproduce the observed non-gravitational acceleration of 3I Atlas rely on the balance between mass loss and inertia. In these models, the recoil force generated by outgassing must be sufficient to measurably alter the object's trajectory. When those calculations are performed using the observed deviation, they consistently favor relatively small nuclei. Many solutions converge on diameters close to 1 kilometer, with some allowing a range between roughly 800 meters and 1.5 kilometers. Within that size range, the required mass loss remains physically plausible under known cometary processes. A nucleus approaching 3 kilometers in diameter occupies a very different regime. Because mass increases with the cube of size, a body of this scale is dramatically more massive than the models assume. The same amount of outgassing that could significantly accelerate a 1-kilometer object would have a far smaller effect on a nucleus nearly 3 times larger. To reproduce the observed trajectory change, the object would need to expel substantially more material, and to do so in a way that produces a net directional force rather than canceling itself out. This would require either unusually intense mass loss, an extreme asymmetry in the distribution of active regions, or a sustained jet-like release of material maintained over an extended period. Each of these scenarios is physically possible in isolation, but they become increasingly constrained when considered together. The required outgassing would need to be both powerful and efficiently oriented, despite the object's large mass and the observed decline in overall activity after perihelion. As a result, the revised nucleus size places strong pressure on conventional non-gravitational acceleration models and significantly narrows the range of viable explanations for the observed trajectory deviation. Such scenarios remain physically possible, but they become increasingly constrained when considered alongside the size measurement and chemical anomalies. The size, composition, and dynamics of 3I Atlas do not present isolated problems. They reinforce one another. Each new constraint narrows the range of viable explanations. There is also a population-level question. 3I Atlas is significantly larger than Oumuamua and 2I Borisov, the only other confirmed interstellar objects observed to date. If objects of this size are detectable, the apparent absence of a large population of smaller interstellar objects becomes difficult to ignore. Detection bias may contribute, but it does not fully resolve the discrepancy. Taken together, the data support a limited but clear conclusion. 3I Atlas does not conform to established models of cometary behavior. It may be natural, but it does not behave like known solar system comets in size, chemistry, or dynamics. Its methane production remains unexplained. Its trajectory challenges mass-dependent acceleration models. Its composition includes metal ratios without known analogs. As 3I Atlas continues out of the solar system, the available observations will be reanalyzed in greater detail. Future interstellar detections may provide the comparative context needed to resolve these contradictions. Until then, the object stands as a test case for the limits of current physical models, and as evidence that interstellar visitors may not simply extend familiar categories, but expose where those categories break down.